Yes, so you should get a notice saying that this is being recorded. And we have turned on live transcriptions. So hopefully you can see the captions. Please let us know in the chat if you cannot or if there's any issue. So I am going to share my screen. And Nance, can I just get an okay that you're seeing this properly? As we had some.
Yes, this is good.
Thank you. All right. Hi, everyone. I am Rutu. I am an astrophysicist and science communicator with the Chandra X-ray Center and NASA's Universe of Learning. And today I am here with my colleague, Nance. Nance, you want to say hi?
Oh, hi, everybody.
So Nance is the imaging scientist for NASA's Chandra X-ray Center. And today we are going to be showing you around our wonderful observatory. And what you're looking at right now is the control room. And we'll talk about the observatory, we'll talk about things we see, we will talk about the control room, and we'll talk about how we use computers to do all of this stuff. So first of all, let's take a poll. You should see a poll turning up on your screen. If you had the chance, would you want to go to space? And I know we have a lot of groups here, which is great. Welcome to classrooms. I guess you can take a poll and see what majority you have in the room. But yeah, we're glad to see so many student groups here. Welcome to everybody. And we're waiting for a few more votes.
We have a very adventurous group today.
Yeah. Looks like everybody who has responded so far wants to go to space. We're waiting for 2 more people, one more group, or one more person. Give them just a few more seconds to chime in. Or, you know, maybe they would rather not answer. So, all right, well, everyone who responded would like to go to space. Wow, this is a very adventurous group. Awesome. So, well, Nance and I are not astronauts. We are actually based in Cambridge, Massachusetts, where the Chandra X-ray Center is. And well, currently, due to COVID, we're not at work. So we're based in the periphery, somewhere around Cambridge, Massachusetts. And we, as I said, we're not astronauts, although we each wanted to be at some point in our lives, but what we wanted to do changed, and that's normal. So what did we want to do? We're going to talk just for a second about how we got here. So I have always loved science and math and just learning about the world around me. But I've also always loved things like literature and writing, which many people often think doesn't really go with science and math, but it does. And I love doing all of that. So I did all of that in school. And then I went to college and I did physics and astronomy, but also philosophy and writing poetry and, you know, taking music classes. Then I went to grad school and did cosmology, which is studying our universe and what it's made up of and how it's changing over time. And, you know, how's it going to end, if it's going to end? Fun questions. And this involved doing a lot of research and data analysis. Basically, I had to take information about all these points of light we see in the sky and make sense of it. And this is where computers and coding come in, because I can't really sit here on my own and make sense of the billions of points of light we can see in the sky. So I have to give a computer that information and tell the computer how to make sense of it. So there's a lot of coding there. But I also found that I missed the philosophy and literature and writing side of life. And so now I have come to the Center for Astrophysics at Harvard and Smithsonian. And I do my astrophysics research, which, as I said, you know, uses a lot of coding, uses computers to make sense of all the data that we get from the sky. But I also get to write and I get to do outreach. And I spend a lot of my time trying to show the rest of the world how wonderful our universe is. And funnily enough, that also includes coding. Like, if I want to show you how we spread out the light from a star and how we can learn from that what things the star is made up of, that requires a computer. I use a computer, I tell it how to make sense of that light and that data, and then the computer can make this pretty picture that'll show you what things the star is made of. So coding is my way of exploring the universe and sharing it with everybody else. And please feel free to ask me a question anytime, and I will pass it off to Nance.
Hi, my name is Nancy Wolk. I have always loved astronomy. I loved amateur astronomy as a kid. And when I was a teen, I joined a group of adult amateur astronomers in Buffalo, New York. We had a nice dark site we could take telescopes to. And I learned a lot from people who really just enjoyed doing this as a hobby. I did undergraduate work, getting a physics and an astronomy degree. And then I decided to stay and get a master's degree in astronomy. And while I was there, I also got a high school teacher certificate. However, I loved astronomy so much, I never did the teaching, but I started working with the Chandra X-ray Observatory in 1996. So if you can do a lot of math, you know I'm old. I've been here roughly since 1996. I decided to learn about computer science in 2000, and I got a 2-year program certificate learning how to program computers. Basically, what I've done with the observatory is lots of different things. I have worked as analyzing images from the spacecraft. I have worked as a science operations person who scheduled when we would be looking at certain objects and to deal with when there's a problem on the spacecraft. And right now I am the imaging scientist, which means I put together those really pretty pictures that you see in the newspaper or for press releases. And I'm going to talk a little bit more about that later. I always see programming and coding as a puzzle that's just waiting to be solved. It's sometimes tricky to talk to a computer because, as I'll mention later, I personally think computers are really, really dumb. So we have to figure out as humans how we want to talk to the computers to make them appear smart. And I'll pass it back to Rutu, but you can ask a question anytime in the chat or in the questions and answers.
Thank you, Nance. So we told you a little bit about ourselves, and now we'll tell you about the wonderful observatory that we get to work with. So Chandra is an X-ray observatory, which means it looks at X-ray light from the skies. We're going to talk about that in a bit, what that means. But it's a space observatory, which means NASA had to launch it into space. And that's the picture you're seeing right now, is a beautiful nighttime launch. And actually, I'm going to let Commander Eileen Collins, who led the launch. I'm going to let her tell you about it a little bit.
I'm Eileen Collins, commander of Space Shuttle mission STS-93. I was also the first woman to command an American space mission. On July 23rd, 1999, my crew deployed the Chandra X-ray Observatory. We had trained specifically for this flight for over 16 months. My crew felt personally responsible for the successful launch and deployment of Chandra. We trained heavily in simulators. We did standalone simulators with our training team, and we also did joint integrated simulations. Leading up to the launch, my crew was very confident that we were totally trained and ready to go. We weren't nervous. We were just primarily focused on doing the best job that we could. That summer, we had 2 launch delays. The first one on July 20th was due to a problem on the space shuttle. And then the second launch delay was 2 days later, and that was due to thunderstorms in the launch area. But we were happy to finally get the launch off on the 3rd attempt the third time that the crew had strapped in to the shuttle, people often ask me, what does it feel like to be in a space shuttle launch? It sounds like you're in a room that's on fire, as you've got the boosters and the engines burning around you in what we call a controlled explosion. There's so much shaking in first stage when you're on the solid rocket boosters that if you try to write, you would not be able to read afterwards what you wrote. We had a successful launch, and we were able to proceed with procedures to get Chandra on its way on flight day 1. So looking back, it was a perfect deployment. Our crew watched the Chandra float away. We took our final photos and our final videos. As we watched Chandra float away, it seemed like it was almost like a sailboat on a calm sea. We knew that no one would ever see the Chandra again, but that we would still feel its presence as it continued to send its data and its information to Earth for many years to come.
I think that's such a cool feeling. Like, how wonderful it must have been to think, you're seeing this thing for the last time that any human being is going to see this observatory. But then that observatory goes and shows the entire universe to all of humanity. Such a beautiful thought. I'm going to follow that up with
I'm Eileen Collins.
I'm going to follow that up with a message from Dr. Belinda Wilkes, who up until a few months ago was the director of the Chandra X-ray Center.
Less than 1 minute away now from the 95th space shuttle launch. 35 seconds. T-minus 30 seconds.
When Chandra went up on the shuttle, so the shuttle basically lit up the sky like daylight for a couple of minutes as it went up, and the ground underneath our feet shook.
5, 4, 3. We have a go for engine start. 0. We have booster ignition and liftoff of Columbia, reaching new heights for women in X-ray astronomy.
We were 2 or 3 miles away. So it's just an amazing feeling of the power that is needed to escape the Earth's gravitational pull, which we needed to do to get in orbit. And also amazing to think that mankind can actually do this. It's very satisfying and exciting to see the results of all the years and all the people who've worked on Chandra, and finally it goes up.
So again, that was Dr. Belinda Wilkes. And here is a little animation of Chandra. We're zooming out from the moon. Fun fact, the word Chandra actually means moon. And this is the observatory. It's about the size of a bus. And Nance will tell you a little bit more about this later when we're wandering around the control room. Here you're coming to the front. This is the hole where light goes in to, create that beautiful picture that we animated inside there. And those are the solar panels open in all their glory, and Chandra is up in space, showing us everything around us. And it shows us many, many things, like we can see exploding stars and what's left over afterwards. We can see what's going on around a black hole. We can see X-ray light from merging galaxies. And we can see much, much more. So, excuse me, I said X-ray light. What does this mean? Why do I keep talking about X-rays? You may have heard of X-rays when going to the dentist or the doctors. X-rays are actually a type of light. So is infrared light. If you've ever used night vision goggles. Actually, here's a poll. Which kind of light have you used or interacted with in your life? If you're not sure, take a guess and, let us know what kinds of light have you, experienced in some way. And we'll give you a few more minutes, or sorry, a few more seconds. Well, we have 7 people or groups who have responded so far. I know we have some class groups, so we'll give you a few more seconds to get your responses in. Very cool. And as you can see, it looks like many of you have interacted with lots of the different types of light. Visible light seems to be the most popular one. Yes, everything we see around us, we can see because of visible light. Because visible or optical light is bouncing off of stuff and coming into our eyes. X-rays, you know, if you've taken, as I said, if you've taken an X-ray at the dentist or the doctor's, ultraviolet light is what gets our skin tanned and sometimes gives us sunburns and is the reason we need to wear sunscreen. Infrared light is actually heat. We radiate infrared light because our bodies are warm. If you've ever used night vision goggles, you're seeing things because the night vision goggles are recognizing where heat is coming from, where infrared light is coming from. So these are all many different types of light. And why do we need all of these types of light? Well, let me tell you a story. Long ago, there was this astronomer named Tycho Brahe. This was before computers, this was before anything. He was just a human being in the 1500s, and he took a lot of elaborate notes about what happened in the sky. And because he took very, very careful notes, he knew where things were supposed to be in the sky. He knew what the sky was supposed to look like. So one day he sees this new star pop up that wasn't there before. He's like, I don't know what that is. How did it get there? He didn't know, but he just made notes saying that it's this new star, new light that has popped up. He made notes of it for about a few months and then stopped because the new star disappeared. We now know that what he saw was actually a supernova explosion. A massive star, a huge star, ended its life and exploded, becoming really, really bright for those few months, and then dimmed away. So now, about 500 years later, we thought, okay, a star exploded, let's see what's left over. And 500 years might seem like a lot, but actually for the universe, it's a really, really small amount of time. So we're like, okay, whatever is left over should still be there. And because Tycho Brahe took really careful notes, we knew exactly where to look in the sky. So we looked where he said he saw the new star, and we saw this, which, as you can see, isn't very interesting. It's kind of like, okay, there are some stars, but not much going on. So then we decided to look at it in X-rays. X-rays are the kind of light that Chandra looks at. And X-rays usually show us the most energetic, explosive things in the universe. So we thought, maybe we should look at this with an X-ray telescope. And we did. And bam, we see this giant ball of tendrils of gas and dust flying out of this thing. There's this giant tentacly cloud over there in the sky that we could not see with just the light that we can see with our eyes. So we put the X-ray and the visible together, and we get a nice, beautiful view of what is called a supernova remnant, what was left over when that star exploded, shown in X-rays, along with the backdrop of beautiful stars that we can see with our eyes. So this is why we need to look at things in different kinds of light, because the different kinds of light show us different parts of all the stuff up in space. And with that, we can see things like star clusters and nebulae, giant, beautiful clouds of gas and dust where stars are born. We can see planetary nebulae. This actually has nothing to do with planets. It's just because way back when, before telescopes, these look kind of fuzzy, so people thought they were planets. But actually, these are stars that have ended their life and have slowly wafted away all their gas and dust. We can see pulsars, these spinning corpses of dead stars that are creating all of this turbulence around where they're spinning. We can see the center of our galaxy. Fun fact, this is our galaxy in optical light, what it would look like if we could get close enough to look at it with our eyes. Then we look at it in infrared to see more dust. We see more of the galaxy. The dust was all very dark when we looked at it in optical light. Then we look at it in X-rays and see a bunch of explosive things happening. What's going on? This cloudy thing over here is covering the center of our galaxy, where the supermassive black hole is causing a bunch of weird stuff to happen around the center of our galaxy. Put it all together, here is a beautiful view of the center of our Milky Way. And this, interestingly enough, is what you were listening to at the start. If you were on at the start and you heard that music in the background. Now, the way we combined these pictures, we have the optical, we have the infrared, we have the X-ray. We told a computer how to merge them together, how to keep the brightnesses and change the brightnesses of the images to make sure that we can see all the beautiful features. And Nancy will tell you a little more about that later. But then we decided that, not everybody can enjoy images completely. Maybe, and maybe there are other ways to enjoy this data. So we decided to turn it into song. The music you were listening was literally a transcript of this image, going from left to right. For each point of light, if the point of light was higher on the screen, there was a higher pitched sound. If the point of light was lower on the screen, it was lower pitched. And depending on how bright the light is, that's how loud it was. So you were actually listening to this image at the very start. And if you weren't here at the start, don't worry, Nancy's going to play a bit of another object like this that we have turned into music. So moving away from our galaxy, you can see other galaxies, you can see merging galaxies. You can even see clusters of galaxies. Every point you see, almost every point you see in this picture is a galaxy. We can look at things so far away that galaxies look like points, and we can learn about them using X-ray light and all different kinds of light. And sometimes these galaxy clusters even smile back at us. Chandra sees all of this because Chandra has made several billion kilometers. Chandra has traveled for several billion kilometers. Chandra has made thousands of trips around the Earth and has collected trillions of bytes of data. Imagine just like, information about all of those points and all of those galaxies and nebulae and everything we saw. Trillions of pieces of data. And that has required millions of lines of code. We have to give computers millions of instructions on how to operate the telescope, how to collect data, how to analyze data. And I'm going to let one of my colleagues, Sabina Hurley, who is the program manager for the flight operations team, tell you about some of the work that needed to get done in order to tell the computers how to work the spacecraft.
They knew the science that they wanted to do. The technology to do it didn't actually exist. Countless engineers had to solve a whole host of problems to get Chandra on orbit. The mirrors on Chandra, those mirrors had to be smooth to the level of a couple of atoms. You're skipping photons, so they need to be atomically smooth. And they have to be really delicately aligned because you need all 8 mirrors to be working together, right? And they are now focusing on an instrument, and the instrument chips are only 4 inches square. And you have to hit that 4-inch square every single time. And that's not actually good enough. That would just give you a blob. So to get the imaging you want, the resolution you want, you have to hit exactly the same spot on that 4-inch square every time. And the spot you have to hit is less than the diameter of a human hair, 10 meters away. Then you have to do this on Earth, but it's going to operate in 0G. So you need to figure out, how can I align these so that they'll be aligned on Earth for testing, But then when it's up in space, it has to stay aligned. You can't go up and fix it. So how do I build all the structure around it so that they stay aligned so precisely through all of that? So once you've done that, you have to make sure that you're controlling the temperature of those mirrors to within fractions of a degree. But you're in space. It's a harsh environment. The engineering and the level of testing and trying and retrying and testing to get just the mirrors right is absolutely mind-blowing.
So that was
They knew that.
Sabina Hurley, and now I am going to turn it over to Nance to tell you about how we take data, how it gets to us, how we process it, and all of that fun stuff. Nance, please take it away.
Hi, my name is Nancy Wolk. You heard me before. So what we're seeing in this slide is kind of an example of how we get information from the telescope back down to Earth. It already drew the lines for us, but you can see we're looking out at a big blob out in space, and the light goes into our telescope, which then comes down to the Earth to one of those giant radio dishes. And then it's sent over. If you look carefully, it says JPL. That is NASA's Jet Propulsion Lab, if I can speak. That is out in California. And then it travels over to where we are, the OCC, which is short letters for the Operations Control Center. And I'm actually going to take you on a quick tour of the Operation Control Center now. So let me take over and share my screen here. There. Sorry about that. My camera was way low. Hopefully everybody can see the control center now. This is where we actually run the spacecraft from. We are unlike the Hubble Space Telescope. We cannot go up to space and fix it if something breaks. So if there's a problem, everything that is done here. And this, when I say here, I specifically mean Burlington, Massachusetts. That's a small suburb, about 12 miles outside of Boston. So when you first come in, we have this big open space. We have on this wall a very neat half-size diagram of the telescope itself. So here's our telescope. The important things that you need to know about is this little funky arrow here. That is our singular antenna that sends out information back to Earth. And this part here, that's like a squarish object, that is the spacecraft. Everything else is the telescope. I'm going to go over to our fun corner. Lots of scientists like to hang out here. And what we have in this corner is a model of Chandra, some pictures of a star forming region that was taken by the Chandra X-ray Observatory. And my personal favorite over here is the flag that was taken up on the space shuttle by the astronauts when they released Chandra. So this flag here actually was up in space. When there's a problem with the telescope, we have this lovely big room that everybody can look in, and they discuss how they're going to fix this problem. And a lot of times this can take a lot of practice and a lot of brainstorming. And I'm going to take you to the room where it happens. So we're going to leave our nice public area where we have people visit. And we're going to head over, excuse me, to the actual control room. Just down this hallway. We have some really nice pictures on our walls in case people want to see those. We'll add the link for this in the chat in a few minutes. And over here is our actual control room. You can see the background that Rutu had up and I have up behind me. Let's go on in. We're going to hop through the window since we're virtual. Over on this side, we have the Command Controllers Council. This is the person who actually sends the commands up to a telescope. What we do is we talk to the telescope about once every 8 hours. Every week, actually every 2 weeks at this point, we have a schedule of observations, maneuvers, and things we want the telescope to do. We send that 2-week schedule up to the telescope. The telescope then works on it without any humans around and will send us the information back every 8 hours. If an emergency happens, we actually have lots of stored commands for the telescope to say, whoa, this isn't right. And it will run one of its stored commands to put it in a safe position so it won't get damaged by the sun or anything else. So we have ways to protect our telescope, even though there's no humans there. So I'm going to go right to the center here. So if we were actually in this room, you see it's kind of like the Star Trek Enterprise. You're up on the bridge, you're standing in the back, you have people working here in 2 rows in front of you. The flight director is up in the right-hand corner, so you can't see where they are right now. But we have some of our subsystems here. So we have to run different parts of the spacecraft, such as you'll see on your right side, it says PCAD. That's PCAD, our pointing and attitude determination. That's how we know where we're pointing the telescope. And that system works all on looking at stars, matching patterns, and making sure we're looking at the right things. The next row is where we have our science teams. So for example, in Sabina's video, she showed you that little 4-inch square. That is our ACIS, Advanced Charge Coupled Device Imaging Spectrometer. It's a lot to say, so we just say ACIS. And this is where the team would sit to work on that if there were issues. The thing I want to show you here is our screens. This screen in particular, we work on the Deep Space Network, which was created for planetary missions, because originally with NASA, the only thing that went out very far were planetary missions. So there's a special system created for that. There's 3 radio telescopes around the world. One is at Goldstone, which I believe is out in the Mojave Desert. One of them is in Australia, and one of them is in Spain. These 3 telescopes are positioned around the world so we can talk to any spacecraft outside of the Earth at any angle. It does not matter because we have these 3 covering the whole sky. And what this is showing us is when we're getting signal down from the telescope and when we send information back up. So that is how we are able to talk to the telescope. And I know we're really close, but all these screens give us information about what we're looking at, what the telescope is doing, and if there's any issues, which is kind of hard to see, but the screen up here, see how everything's nice bluish green? That's good. We want to see bluish green. We do not want to see red on that screen. So this is our control center. And what I'm going to do is take you back to our presentation and kind of discuss what happens when we get that data back down from the telescope. So I'm going to switch my screen over here. So again, this is that animation. We see something in the sky. It goes over to the telescope. Down to this one, I'm going to say is gold. I don't know which one that is. I'll just say there's a telescope there. Over to JPL and then back to our control center. What do we get back? We get back 1s and 0s. If you remember earlier, I mentioned that computers, in my opinion, are very dumb. Original computers were electrical circuits, and they literally understood, I'm on, I'm off, I'm on, I'm off. On it's a 1, off I'm a 0. So we started working with binary code. That's base 2. So unlike how humans count, which is 0 through 9, base 10, computers speak in 2 numbers, 0 and 1. And when you want to talk about something bigger than 2, you have to use the next place over. So what you're seeing here is what digital code looks like when it comes down, binary code. Now, this doesn't make any sense to us. What we do is we will break this code up into different segments so that we can understand what we're looking at here. Oops. So if we talk to machines, this basically goes with what I just said. Binary code is on and off, very simple. And you see this nice little packet of zeros and ones down here. We can convert that to something we see that's more human readable. The first section of that zeros and ones tell us what time we saw something on the telescope. And then the X and Y will tell us what position on that little 4-inch chip did we see this. And the very last thing tells us how strong, how much energy was in that. And from that information, we can do this and take that information and make a pretty picture. Because we now know when the light came in, the X-ray light, we know where it fell and how much energy there is. So this works a little bit like the cameras in your cell phone. I assume everybody's seen cell phone photos. The big difference here is this is black and white. Your camera with your cell phone is in color. And you're probably thinking, wait, I saw a picture earlier that Rutu showed that was in color. That is true. First thing we do is we can apply different color maps to that black and white. This remnant was the very first real observation we took, where we pointed the telescope and tried to look at something. This is a supernova remnant, very similar to the Tycho supernova remnant. And this was the first time that we saw, I hope you can see my mouse. Do you see this little point in the center? That is the leftover of the star that exploded here. And if you notice, this looks very different than the Tycho supernova remnant, where that was beautiful and fluffy and very, very round. This seems to have a little different structure to it. Well, we wanted to learn more about that. And what we did is we were able, ooh, this looks very different. Same thing. What we've done here is we looked at that last bit about energy, and we could determine what we were looking at. For example, when we see iron in X-rays, iron gives off light in a very, very specific energy. And same with calcium, silicon, sulfur, and I'm trying to remember the last one we used here. I can't think of it off the top of my head, I apologize. But basically, we could split up the image into different slices. One slice, the deepest red, was telling us, here's where the silicon is. And the purple is where the iron is. And the green is where the calcium is. And this blue ring around the outside edge is what we call everything else, which is basically the blast wave. That's when the star first exploded. Where did the energy go? It goes out in that blast wave. But if you notice, this looks very, very different. And in the background, you'll see all these yellowish orange stars. That is the optical image. There's really not much here when you look at it in optical, very much like the Tycho supernova remnant. But here you see all sorts of structure. Can you tell that there's this black segment here? There's not much stuff there. We're not sure why. But if you look over to the side, there's some jets of material. We also don't understand where those came from. And there's actually jets on the other side that are moving away from us. Oh, yes, moving away from us. What I mean by that is we can tell if the light is coming towards us or away from us, because there'll be a subtle shift in the energy. I'm going to guess that most of you have heard a police car or an ambulance go by, and sometimes it makes a funny sound when it's coming towards you. It's more high pitched, and when it goes away, it's a little lower pitched. That's because it shifts as it moves. Same thing happens with light. So we actually know not only what this is made of, but where everything is in 3 dimensions. So we can take this this two-dimensional image and make a 3-dimensional model. And again, this is all through software. We were able to plot out where the different parts of gas are. These are those funky jets I was showing you. The different colors are different elements. And the light blue in here, I'm going to play it one more time. That kind of lightish blue-green on the outside, that's more of the blast wave that you saw. So we're able to actually go from zeros and ones to a 3-dimensional model. And not only that, we can print that model. So here's a 3D print of this supernova remnant. And then you can actually go and see this in virtual reality. And we'll be putting up links later about that. So if you have a 3D printer at your institution, or if you have virtual reality goggles, or somebody who's good with this on a telephone, you can actually look and step inside a supernova remnant. And all this is available because we have taken computers and processed the information in several different ways. As Rutu mentioned earlier, we also have learned how to make these images talk to us or sing to us. I'm going to show you an example here. This supernova remnant we've been observing since 1999. So that's a bit of time. That's over 20 years. And what we've noticed is we can actually see that it's still expanding outwards. And what this is going to do is show you how you can listen to it expanding outwards. So if everybody can listen.
Nance, we can't actually hear you. Nance? We can't actually hear you.
Oh, you can't hear it?
No.
Okay, hang on a sec. Oops. Hang on a second. Let me fix that.
My apologies. Now let's see if you can hear it. That's better. I hope you could hear it this time. What we've done here is you could see that as the little circles of information were going over the data, it would get louder and quieter depending on how dense the material was. So it's another way of representing the data, because just because you can't have perfect vision doesn't mean you can't explore space. We're trying to make everything accessible to multiple people. And if you have vision impairment, not a problem. We're going to work on that. We also do a lot of our 3D models for people who have vision impairment so they can actually feel what these objects look like. And again, we can only do this with computers. Now I'm going to go back to Dr. Belinda Wilkes, and she's going to talk a little bit more about the observatory.
We are on this tiny little planet next to a very ordinary star that's in the middle of its life, in a fairly normal spiral galaxy in some corner of the universe. And the universe is huge, and there are billions and billions of stars and billions of galaxies and supermassive black holes. And yet we are sitting on this Earth, and we're able to understand at least some of what we're seeing by just looking.
And
we are on this.
Now I'm going to pass this back to Rutu, and she's going to talk about the different computer languages that we've used to help program the telescope.
Thank you, Nance. And just so you know, all those wonderful tours that we took, I just put the link to those in the chat so you can go do them yourselves. In the meantime, let's take a poll. Let us know if you've ever tried coding. It can be with any language, however simple or complicated. Have you ever told a computer how to do something?
And by the way, Rutu, you will have control if you share the screen again.
Yes, thank you. I am just getting that back up.
And any type of coding, it could be as simple as the little turtle coding, HTML, which is writing web pages. Got a couple people.
Yep.
So I'm going to end the poll.
Right. Looks like everybody who answered has tried coding. So that's very cool. There are many possible languages you can use. Many people nowadays like to use Python because, first of all, it's open source, so it's free. And people develop a lot of libraries in Python like AstroPy and CosmoloPy, which will do astronomical calculations for you. And that means that we don't have to reinvent the wheel every time we want to go and tell a computer what to do about data from the sky. We can use and build on what others have done. So yeah, these are some of the coding languages that are used. And yes, you just took a poll. And now I'm going to talk to you a little bit about, oh, if you can hear my dog barking, please excuse him. He seems to start barking right near the end of every session. I don't know why. But you know, dog's gonna bark. What you gonna do? So we're gonna talk a little bit about some of the resources we have, some ways that you can explore X-ray astronomy and coding even more. These are resources from the Chandra X-ray Observatory and NASA's Universe of Learning. And I'm just going to switch the screen I'm sharing for a second and take you to my browser. So one of the things we have is this thing called How to Talk to a Spacecraft. It is this activity with binary code. It's an hour of code activity, and you can create binary bracelets. You can even create music based on binary code. So that's one thing. Another activity we have is called Recoloring the Universe, where you can learn about how we create these beautiful pictures. And you know, this is a video-led activity, so you can actually play each of the YouTube videos and code along with it. There's basically a tutorial leading you along on how you can change the colors and represent different types of light in different colors. You first start with simple images like a square and some flowers, and then you get to supernova remnants and other objects in the sky. This is also an hour of code activity. One more hour of code activity is on Tinkercad, which some of you may have used. It is software that you can use to render things in 3D, to bring in data and make your own 3D model of it. And again, you know, you can start with basic shapes and things, create some complex objects, and even pull in NASA data on supernovae and make your own 3D model online of what that supernova looks like. And then if you have access to a 3D printer, several libraries do, some schools might, you can then print those 3D models. And we actually have several templates, several files that you can just directly print, and you can get these models of, say, an exploding star, or another one, the Cassiopeia A that Nance was talking about, pillars of creation, which are a nebula. We have a bunch of different 3D prints available that you can just download the file and print if you have access to a printer. Another thing you can do is take your own image and process your own image of something in space. Now, I'm talking about all of these. We're going to put all the links in the chat so you don't have to worry about like trying to copy down the links from anywhere. This is called Observing with NASA, or Micro Observatory. And the link that we're going to put in the chat will lead you to this page. And you can click Control Telescope, which will let you, it says select your target. You can have one of our 3 telescopes around the world take your very own image of something in the sky. And we've got like solar system objects like the moon and Venus and Saturn. And as you can see, Mars is not going to be available tonight. Mars isn't going to be up in the times where our telescopes can look up at the sky at night. So this will tell you what you can look at on any given day. You can look at the center of our Milky Way. You can look at star clusters. You can look at other galaxies. And then you can process that image yourself in that same software that Nance was telling you about. So actually, if you for a second just look at my video here, I'm going to stop video. This picture you see is an image I had Micro Observatory take for me of the Pleiades star cluster, and then I processed it myself. So you can do that. And you can also work with pictures that have come from NASA data. So there's this thing called NASA's Astrophoto Challenges, where you can combine data from NASA about light, many different kinds of light from one object, and create your very own picture of that object. This is the page that, this is the software that Nance was talking about, where you can, change the brightnesses and change the contrast and make your own version of this. Well, this is the M82 Galaxy. So yeah, you can make your own version of the M82 Galaxy. And currently the NASA Data Challenge is closed, but you can still work with the images. You don't have to the challenge doesn't have to be going on. But later in the year or next year, when the challenge comes back up, you can then submit your results and maybe get highlighted. These are some of the results from a previous challenge. You can also use this resource called ViewSpace, if I can reach my tabs, where you can scroll around and see this is a galaxy in optical light, the way our eyes see it. This is what it looks like in X-rays. Then you put them together, and this is what it looks like. And the interactives up here have a lot of different ones of these, and they also show you how computers make sense of this data. There are many different types of interactives. So please go ahead and explore. And another thing to explore is the AR app, Reach Across the Stars. You can get this app on your phone, and it's as if you'll be having a conversation with some of the great women in science of our time, and slightly before our time as well. And there are also some experiences like you can wander around Mars, you can learn about the science these women did and learn about their lives as well. And then, you can take your own selfie about future astronomer, future biologist, whatever you want to do. You can do all of that in the app. So those are some resources, and we're going to put all the links in the chat. And we will close off with a word from one of my colleagues. And actually, it turns out I should have forwarded through these. But we will close off with a word from Dr. Daniel Castro about all the cool things we can learn from Chandra.
We didn't know that stars could emit X-rays, for example, and the way they do it. We didn't understand how stars blew up. We didn't understand black holes in nowhere close to as much detail as we do now. We don't understand the clusters of galaxies that make up the web of space-time in the detail that we understand it now. Chandra represents a huge step forward in astronomy in general.
And with that, we can look through our universe with Chandra. Here are links that we will also put up, and please let us know if you have any questions. You can put it in the chat or in the Q&A. And all the links, thank you, Nance, all the links are in the chat. We know it is the top of the hour, but we will hang around for a bit longer if anybody has any questions. So feel free to ask. And thank you all for being here.
Yep, thank you all. I just added that to the chat. If you have any questions, you can reach out to Rutu or I. We will be here for a little bit. Thank you very much for joining, and I hope you guys like this. A question, has anyone seen inside a black hole? That's a really good question, and the answer is absolutely not. The whole trick to why a black hole is called a black hole is because the gravity on a black hole is so strong that not even the fastest thing we know, which is light, can escape it. So we really only know where black holes are from material falling into the black hole. We never actually see the black hole itself. And in X-rays, what we see are the gases swirling around the black hole just before they fall in. They're swirling so fast, they get really, really hot and give off X-rays. But that's a really good question. Thank you, Julie.
Yeah, I think many astronomers dream of being able to see inside a black hole, but we do know that that would break the laws of physics, and
You're welcome.
unfortunately. Any other questions?
Sometimes I wish they hadn't named it a black hole because it really is just a star.
Yeah.
It's just a very, 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 very dense star.
Yeah. Yeah, black hole makes you think like, oh, there's a hole in space. No, it's just a lot of stuff squished into a very, 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 as Nan said, very, 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 very small space.
Yes. Well, thank you all again for joining us. I don't see any questions or on the chat. Okay, have fun heading home for the day. We were told that you will get a copy of this recording or a recording afterwards. So if you don't, please feel free to reach out to the observatory and we'll make sure you get a copy. Have a great day and thanks for joining us.
Have a great day, everyone. Thank you. And keep looking up.